So we had seen a few concepts on multiplexing, right? And we had looked into how important communication plays with regards to human existence, and the technological upgrades that are done in the field of communication. So not only we looked into CDMA, right, code division multiple access, but then we looked into SDMA also, right, space division multiplexing, and CDMA and TDMA, time-based multiplexing. Okay, so now that we are clear with all of these concepts, right, um, we will move on to a problem, right? So a TDM system has 12 channels and employs a channel time slot of 6 microseconds. Calculate the sample rate for each channel. So you might come up with some problems where the time slot is given, okay, but then uh, you will have data of number of channels, but then you'll have to calculate the frequency. See, whenever there is a rate, okay, sample rate, it's always referring to frequency. Keep this in mind. Okay, so whenever there is a sample rate, it means that it's always referring to frequency. So this formula is important, where Fs is equal to 1 divided by n into Ts, okay, where Fs is referring to the sampling rate, and n is the number of channels, right, and Ts, right, we have 6 microseconds, the channel time slot. Okay, fine. So if you calculate this, right, so you will be getting about 13.88 kilohertz. Can someone verify that for me? Is the value proper?
Yes, sir.
Yeah, thank you. So we get about 13.88 kilohertz, right? So this is going to be my frequency at which, for this combination, um, 12 channels, then 6 microseconds time, right? So for this combination, there's going to be a frequency of 13.88 kilohertz. See, ultimately, you should understand communication is all about combinations, right? How you sample the signal, and how far you want to propagate the signal. So that is based on the frequency, and um, what group that you're serving. So when I say what group you're serving, which means should the network be reliable, ultra reliable, or it's okay just to have a network, right? So based on that, systems will be employed, and accordingly the transfer rates also does change. Okay, so ultimately we are looking at a better communication facility, okay, where we can look at zero delay and 100% communication, noiseless communication. Okay, so the number of channels in system, okay, so now what we will do is we will change it. Okay, so we will change to number of channels to 14. Okay, so here we had about 12, so we will increase to 14, and we will see what happens for the new values. Okay, how the new values are impacted. So calculate the new value of time slot. So here they want us to calculate the time slot. If the sampling rate remains unchanged, so we are going to keep the same sampling rate, which means 13.88 itself is going to be used, and we are just going to find out the slot, the time slot, right? So just one unknown data. So, and number of channels are changed from 12 to 14. So we are going to use the same formula, right? Just that TS and FS are interchanged, right? Because they are cross multiplied, and I get 1 divided by n is now the new number is 14. Okay, previously it was 12 into Fs. So we already have calculated the value of Fs, which is 13.88 So that comes down here, right? And you should be getting about 5.14 microseconds. Is the value proper? Please check. You can multiply this and you can take an inverse. 14 into 13k, 13.88, and you can take an inverse. You should be getting that value. Are we getting?
Yes, sir.
Okay, fine, good. So you can see that, the time slot. Now, how do we analyze this problem? Now the channels have increased and you can see the time slot has reduced. So here it was 6, and of course we are using the same frequency, isn't it? So you can see that, the time frame has changed from 6, it has come down to 5.14. Okay, that's because of the number of channels, right? Now the second case, if the sampling rate is increased to 18k, so which means now let us see if I increase the frequency to 18, and my number of channels are going to remain as 14, and I have to calculate the time slot. Okay, so let us see how it goes. So which means I'm going to use the same formula, right? 1 divided by 14 into, and the new value now is 18 kilohertz, right? So 18 I'll be substituting here. And can someone verify and tell me if this is proper? If we're getting about 3.96.
Yes, sir.
Okay, fine. So 3.96. So again, here, what do we understand? Increasing the frequency, right? So between this two number, subdivision 1 and 2, we see that number of channels have remained the same. Okay, only the frequency has changed, right? So due to which the time slot also changed. So you can say that frequency, time, and number of channels, all these three are the combinations here. Okay, so if one increases, the other one will decrease. If one decreases, the other one will increase. So together they work in as a team, like I could say, where proper communication happens. Fine. So moving on, what are the benefits of using time division? Number one is noise reduction and cable plant utilization costs. So how do I say that noise reduction? So noise reduction is because for each they are time based, isn't it? So if I'm using just for a certain amount of a channel will be allocated or given to me only for a certain period, right? After that, immediately I will be taken off, and that channel is reallocated to someone else, right? So that is one way. And cable plant utilization cost. So you don't have to, suppose say you have 100 customers, and you don't have to keep all the 100 customers connected throughout 24 hours, right? So you can probably give them 1 hour time slot or 1.5 or 2 hours. I don't know, these days probably they've increased the time limit to 1.5 hour or 2 hours. How much is it? What's the time limit now? After what time does the call get disconnected?
So each service provider has a different type. Sir.
Different type, right? Yeah. So I
Yes,
guess
sir.
probably it's about like 1.5, 2 hours, right? From 1 to 2 hours. It ranges from 1 to 2 hours, right? So so in this way, what they're trying to do is, they try to give services to many users, okay, having the same infrastructure. So that is one way in which you can understand, right? And do by doing this way, it is just like, you can take example of the lab setup, right? For our lab setup, what do? We have certain equipments, and then we call you all batch wise, right? So it's the same way. It's like a time slot, right? For certain time slot, certain users are allowed, and then after the time slot, then those users will have to give those channels to their other fellow users, right? So it's in that format. So the utilization, becomes higher, and of course the costs come down. You don't have to invest in, say for 100 users, 100 equipments. No. Fine. Then
So how would it work for like
huh,
different companies? Like if I call from a different company and to another phone,
huh.
which company server would it use?
Calling,
Would it use my
calling,
company server or the other calling
calling,
server?
calling. Yeah. There is something called, destination calls, right? So say operator A, okay, and operator B. Okay, so from operator A, the call has originated and it has gone to operator B. Okay, so once the call gets terminated, okay, operator A has to pay certain amount to operator B. Okay, the source from which the call originated. So they have to pay certain amount to operator B. Okay. Say for example, call gets originated from B and the destination is A. In that case, B will pay certain amount to A. Okay. So these are called, service charges, right? And between these operators. And now with regards to time limit also, okay, time limit also, from where the call has originated, either from A or B, okay, those rules will apply. Say operator A has about say 1.5 hour. Okay, let's stick with 1 hour. Okay, he has kept the time limit as 1 hour. So with 1 hour, okay, even though operator B supports for 2 hours, okay, uh, but then since the call originated from operator A, right? So the call will last only for an hour. So you can understand that the source, okay, wherever the call originates, the source, its rules apply. Okay. I hope it is clear.
Yes, sir.
Fine. Now let's say the other way around. Okay. So if the call originates from operator B, then you'll be given a channel for about 2 hours. Later on, your call will get disconnected. Right? So it depends on which operator that your call gets originated. Okay. Then we also saw these PAM, PWM, and PPM, right? Very interesting concepts where we look at amplitude, we look at width, and we look at position, right? So even these we discussed in detail, right? And we spoke very much about the duty cycles, 10%, 50%, 90%. Right, so the ideal is to be about 50%, right, and 50% duty cycle, where you can find on and off both are symmetric, right? So you can find the width of on and off, right, both to be same. But here on is less and off is more, right? And here on is more and off is less. So we would always stick to this, midpoint, where we have 50% of on and 50% of off. Okay, so here in this ppm, right, position, we take out the average of a waveform, and accordingly the waves are either moved to the left or to the right based on the amplitude of the message signal. So message is here in m of t, right? That is message with respect to time. So that becomes a continuous time signal, just like our human voice. So that's also an analog signal, right? Because it varies with respect to time. It's not a digital signal. But this transmission that is happening, from my end to your end, okay, in between, the transmission is in digital format. Okay. So we've seen this, and yeah. I think now we will have to look into a concept which is called sampling and aliasing. Okay, so what is meant by sampling? Now, usually, they say these many samples for these seconds, or so many samples per second. So what do you understand by this? I think DSP all of you are going through, right? So what do you understand by number of samples per second? What is it denoting?
So the converting of analog signals to digital signals.
It's not about conversion, but then it's looking at how many samples that we are taking. Yeah. So when you talk about analog to digital, yeah. So if you
The
take
number of
more
conversions taking place
samples,
per
correct,
second or something.
correct. So if you take more samples, right, so you will have more data, right? So if you take less samples, then you're not probably going to get a proper information, say from 0 to 30 seconds. Okay, so from 0 to 30 seconds, if you're taking about, say, 2 samples, then in between, right, you do not know what is going to be the data from, say, 15 to 18 seconds, right? So you do not know. You might take probably initial part and the ending part. So in digital, what they do is they try to average it out and pass the information. But in analog, that is not the case, right? You have information at every point of time. So that's why it's called with respect to time, which means at every instant of time, okay, there is information. You have information at 18th second or 18.2 second or 18.5, right? So at any point of time, you can extract information from analog systems, right? Okay, good. So we are looking at samples here, right? So samples, the more the samples, the better, because we will have more data and we can analyze more things, right? Okay. The only provision for exact reconstruction is that two conditions, right? So if I have to reconstruct a signal, okay, so from the source, I have some information being passed, and at the destination side, that needs to be decoded, encoded, decoded. So this is also sometimes referred to as reconstruction. Okay, so whatever information, see, because as I told you, I am my voice is analog, and then it's being passed through a digital format, and through the digital format it has to come and reach you, right? And there's going to be a lot of conversions here, analog to digital and then digital to analog, and then that gets into your system probably through your RJ45 pin, or probably through your Wi-Fi card, right? And through the Wi-Fi, the signals are transmitted between your, say, cell phones, or probably your systems or laptops, right? So there's a lot of communication happening from one end to another end, right? So all this happens in a split second. Okay, so that's the advantage of moving on from one generation to another generation. Now, if you're aware, research has already started with sixth generation, 6G. Okay, right now, the world is about to experience 5G, right? Maybe few parts of the world. Okay, it's just implemented, and it's all in trial basis still, right? And the only thing that all are concerned is because of the high frequency usage. Now, what will happen because of this high frequency usages? There will be a lot of samples sampled at each second, right? So which means a lot of information going from source to destination, and as an acknowledgement from destination to source. So due to which, what is going to happen? It's going to take a huge toll on your battery, right? So your battery technology should actually mature in such a way that you should be able to last at least for a single full day. On one charge, you should be able to last at least for a single full day. So a lot of R&D is happening, and if you want to pick up projects, right, so you can pick up in the field of power consumption, right? These days there's a lot of migration happening from the conventional IC engines, right, the internal combustion engines, to electric vehicles, right? So there's a lot of R&D put in where you get your range. Okay, one single charge these days, very common to get about 180 to 100 kilometers. But what if you can double it, or probably you can increase it by about 20-30%? Then your product becomes much better, right? People would like to take that, because all have this battery drain anxiety, right? The stress, they have in mind that what if on the way the battery gets over, and then I'm not able to reach my destination, right? So this kind of anxiety is there. So when we put in a lot of research in this field of power consumption, right? So that's when this technologies will mature and move to the next higher level. Okay, right. So let's get back to sampling and aliasing. So the more samples we take, the better for us to reconstruct or make the image, make the source or message, reconstructed in a much better fashion. Okay, so the signal must be band limited. So I cannot just say from 0 to unlimited frequency, just like how you have op-amp, right? You have infinite bandwidth capability. So I cannot do that here, right? So I should have a specific range of frequencies where I'm going to work from this point to this point, right? So the signal should be band limited. This avoids spectra with infinite extent that are impossible to replicate without overlap. So the reason why we are doing this is so that 2 or 3 signals would not overlap. They are having different frequencies. The sampling frequency Fs, okay, just like how we saw in the problem, sampling frequency Fs must be greater than twice the maximum frequency. Okay, so this is nothing but called the sampling theorem. I think you would have studied in your DSP. Have you, students, sampling theorem? DSP, have you studied sampling theorem? Digital signal processing. The sampling frequency is 2 times FM, right? The maximum frequency. Have you come across this concept? Yes, no? Okay, fine. So whatever is the maximum frequency, right? Suppose we have 5 kilohertz as the maximum frequency, right? And my sampling should be 2 times. So which means it's going to be 10 kilohertz, right? So this minimum sampling frequency is known as Nyquist rate. Okay, it's the minimum distance between the spectra copies between each bandwidth Fmax, that is maximum frequencies. Fine. If the two reconstruction conditions are not met, then sampling theory predicts that exact reconstruction is not possible. So if you're not maintaining this, greater than or equal to 2 times FM, then what is going to happen? Reconstruction is going to be a challenge. Okay, so if it becomes a challenge, then it is telling me that I cannot get the proper message signal. So whereby few information might be lost, just like you say while you're on call that your voice is breaking, right? Why is it? Because your voice is actually transmitted in the form of packets, digital packets, right? There can be chances that few of these packets can be lost. So when these packets are lost, right, that's when your voice goes off for a certain amount of time. Okay, so this phenomenon is known as aliasing. Okay, so that where reconstruction is not possible. This phenomenon is known as aliasing. So it occurs when signals are not band limited. So when signals do not have band limit, okay, then we refer to that term as aliasing. Or when undersampled. So if in case we are not meeting the sampling theorem, right? If we are not meeting the sampling theorem, then it comes up to a new concept called aliasing, right? So what is the sampling theorem? Your sampling frequency should be greater than or equal to 2 times the maximum frequency, right? So are we clear with this concept? Yes or no? Fine. So in either case, there will be unavoidable overlapping of spectral components, right? So I want you to look at this figure, right? So here you have your original signal, which is actually black and bold, right? And samples are collected at different points of time: 1, 2, 3, 4. So at different points of time, samples are collected, right? And aliases, which means, you can probably say that a substitution, right? Or something, which is substituting. So you can find that, there are many aliases, right? Which is actually replicating the original signal. Okay. Assume that a digital data set representing a signal sample value sequence is given. It can be shown graphically as in the figure. These signals might be used for reconstruction of original analog signal may belong to. So I can actually make use of these signals, okay, these aliases, and with the help of these samples, I will be able to know that, okay, fine, this is my sine wave. So I'm going to reconstruct. I'm going to just connect these dots from one point to another. Okay. The sine function one, okay, which is shown in black, right? So I've shown that in black, is found to be fitting the data. However, if the reconstruction process is continued, it becomes clear that there are other sinusoids at differing frequencies. So if in case I don't make that, sampling fs, sampling frequency is equal to or is less than or equal to or greater than or equal to 2 times of fm, when I'm not satisfying that sampling theorem, right? So the frequency does change. So if the frequency changes, the width of this signal changes. So this is the signal, the one in blue, right? So you can see this has one frequency and the other one in green has another type of frequency. See, even though they are sinusoidal waves, but then because of the change in frequency, the width of this signal also does change, just like how we saw in the problem. Just having the same amount of channel and increasing the number of channels, how it varies the frequency, right? So you can see here the time slot, right? And here it's 3.96, 5.14. So we are looking at changes that happens in the message signal m of t. So m of t gives us the signal, right? And based on our sampling, how much of samples we take and at what frequency, you can find different aliases coming up if in case sampling is not met. So it is just like this. If you're not maintaining that standard, there will be many more substandard waveforms. Okay, so these are those waveforms and those are called aliases. Any doubts here, students? Is it clear? What is an alias? Yes, can I have a response?
Yes.
Okay. Fine. So, yeah. So the sine function, okay, is to be fitting the data. However, if the reconstruction process is continued, it becomes clear that there are other sinusoids at different frequencies. Okay, all these frequencies are aliases and overlapping of them is called aliasing. So these different waveforms at different frequency are called aliases, and the process of these aliases getting, combined and, overlapping is called aliasing, right? So the process is aliasing, and those different signals are called aliases. Aliasing results in an uncertainty, right? So if we have so many signals, connecting with each other and, overlapping with each other, ultimately our, message is going to get lost. So I do not want that to happen, right? I just want one signal, and that should be transmitted without any problem. So if I have many replicas, then my system gets confused. It will not know whether, this is the real message signal, or probably it has to follow this blue waveform or probably follow this green waveform, right? So it's like, I'm confusing my system. So it results in uncertainty. Okay, looking at these frequencies, it is difficult to find the right one. So finding the right one is important. Just like, you have many products coming up, and it's very hard to differentiate which is the real one and which is not the real one, right? So, that becomes the problem, right? Evidently impossible to say if some additional information is not supplied. So there can be chances that few of the information can be lost, and ultimately we are looking at losing information. Okay, fine. So it has been proved that there will be no uncertainty if all frequencies above a certain level are filtered off the original signal by a low pass filter. Okay, so again, how do we design a low pass filter? With the help of a resistor and a capacitor. Okay, so we will look into that in our upcoming sessions, how these filters are designed. Okay, so if I can filter out these frequencies, okay, these signals at a certain point, okay, then it's going to be easy for me to take the signal that comes out from the filter. Okay, so that becomes a pure signal. So that is actually what is required by famous sampling theorem. So that limit, okay, where it is 2 times FM, okay, 2 times the maximum frequency. So if you can sample this at a higher rate, okay, which is 2 times maximum frequency, then I can filter it out, right? So it is just like this. If you can't see them, how can you filter, right? So you need to magnify them, you need to increase the frequency, and then you can filter it out with the help of specially designed low pass filter. Okay, so to sample a frequency at least twice higher than the signal, okay, or the frequency present in the signal spectrum. So that is actually referring to our sampling theorem. Okay, so this is the importance. You can make sure that these aliases are taken care of. You can make sure that you are looking at your message signal alone and there is no disturbances at all, right? So students, do you think sampling theorem is really important? Is it necessary for communications? Yeah, it's important, right? Okay, so so whenever we are looking at communication, right, a proper communication, we need to keep all these factors in mind, right? No one would like to have a communication where he or she can hear his own voice, or probably the network isn't consistent, and probably he or she is not getting a proper data transfer. No, we all need proper networks, proper connectivity, proper data transfer, proper communication, a reliable network, right? If I have to put it all together, we need a proper reliable network. Okay, so all this is possible only when we follow these rules: sampling, right, and training our systems which signal to take and what not to take with the help of filters. Okay.